Okay, thank you everyone. I'll give 1 more minute. There is coffee here and some cookies if you want, and we'll start like in a minute.
Yeah, no, Ramon, we have actually a team who works on this. So we also responsibility. Well, I want to talk about, so there are hundreds of at this point, 15 institutions. And I'll talk about doing this internationally. We have a large set of studies. Yeah. Though he doesn't do so much law, he's in our corporate partnership program. He is trained as a lawyer. Oh, okay. But at Columbia? But he didn't see you have it also. Yes, I'm working on it pretty closely together.
Okay, so I think we're going to start. Welcome, everyone. Thank you for attending the October Policy Speaker Series. This is from NASA's Carbon Research Program, better known also as the Carbon Monitoring System. I would like to welcome today's speaker, Stephen Hamburg. He's the Chief Scientist for the Environmental Defense Fund. Stephen plays a leading role in EDF research efforts, including work on quantifying methane emissions from the natural gas supply chain and the use of emerging technologies in improving our understanding of air pollution and related impacts on human health. The title of today's talk is Methane Emissions from the U.S. Oil and Gas Supply Chain, employing an unusual partnership to get rapid and comprehensive results. The talk will introduce us to the efforts being coordinated by EDF for the last couple of years to better understand and measure methane emissions from the U.S. oil and gas supply chain. And we will also hear a little bit about EDF plans to develop and launch MethaneSat, a new satellite to be built that will identify and measure methane emissions from human-made sources worldwide. This talk and Stephen's visit to Goddard intends to continue the discussion about further collaborations opportunities between the NASA carbon science community and EDF in the topic of methane emissions monitoring as well as related topics. We're going to have the opportunity for a Q&A after his talk. So without further ado, I leave you with Stephen. Let me give you the...
I can just hit the... Oh, all right. Great. Thanks so much. It's great to be here, and for those of you online. It's a little harder for those online, but feel free to wave your hand. I spent the bulk of my career as a professor, so questions during the talk are encouraged and welcome. I'll try and make sure there's plenty of time at the end as well. So I'm going to talk about... Oh, I get a little bit of feedback here, so we'll have to see. I'm going to really describe fairly briefly, because of the body of the work that we've been doing over the last 6 years on really, I could say really the last 8 years, in digging in on the role of methane, and in particular how methane and the oil and gas supply chain interact. I'll talk in a minute, but this picture that's in the title slide, which is a bit faded out deliberately, is of a Google car. I will talk about the unusual partnerships that we've used. So we've had an ongoing partnership for almost that long, for 6 years with Google, collecting real-time methane data and mapping methane emissions from local low-pressure distribution systems and quantifying it for the first time at scale and making all that data public. So I think, as most people know, but again, I want to assume in terms of background, Methane is a potent greenhouse gas. It's basically 120 times more potent on a pound for pound when it's emitted, but it's a short-lived climate pollutant. And if we look at the radiative forcing caused by greenhouse gases, anthropogenic emissions of greenhouse gases, you'd say it would be roughly 1/4 of the total warming. But in fact, if we think about it in a little bit more subtle way or a little more integrative way, if we think about methane, it's generally not co-emitted with coolers. And if we think about the coolers that are associated with CO2 and fossil fuel burning, in fact, if we were to mitigate and eliminate that 24% of methane today instantly, which we can't do, it would reduce the warming we're experiencing by almost half, because there is no co-occurring coolers that get emitted when we emit that methane. So it's pure mitigation of warmers. When we mitigate many of the much of the CO2, there are associated coolers, and you actually don't see the net warming is different than the gross warming. So methane is an incredibly important part of the warming puzzle. Now, when I say that, I always have to make sure to be qualified in the sense we're really talking about what I call the and proposition. We really have two climate problems. We have to solve both of them, but we have to solve them in parallel because they are different and their solutions are different. We have short-lived climate pollutants and long-lived, and the solutions to how do we get the net benefits of reducing them are not solved the same way, and we have to do both. So if we just focused on short-lived and not long-lived, we're in bad shape, and vice versa. And one of the things to do that is we have to remember about time. So traditionally, I have a war on CO2e. I think it's a really detrimental concept because we're now thinking about everything in 100 years, but not all the problems are 100 years. So we had a paper in Science about a year and a half ago in which we advocated using a two-tiered numbers. Everything should present at 20/100. Whenever you do a calculation, you really need to think of it in the short term and long term. While 20 and 100 years may not be the perfect time periods, are so well established and they roughly cover what we need to. I make this point because it's really important to think about time. Climate is a time-dependent problem. There is no single solution. So you have to integrate that in there. So we got interested in methane and the potential, and James Wang's here, and James was part of that initial thinking, recognizing the analytics were not well developed in thinking about it, and that we really had to understand how methane emissions intersect with both the larger problem and some of the specifics. So oil and gas, as I mentioned, methane causes about 25% of the current global warming. Note that I didn't include the word net. And the oil and gas sector is roughly responsible for about 1/4 of that. So roughly 6%. And when we started this work, we thought about how does methane emissions from the natural gas supply chain influence fuel switching and its net effect on the climate. So we developed this. There was a paper in PNAS that came out in 2012, and the basic idea here is if you look at the y-axis, this is the amount of emissions from the supply chain and the years of benefit. So I'll just walk through coal. If you have emissions greater than 2.7% of the supply chain, of more than methane, 2.7% of methane is emitted across the supply chain, and you switch from coal to gas, you will not get any net climate benefit over the short term, but over the long term, you'll get a lot. All right? And so it's not a binary. It's not which is better. It's which is better over time. But there's no reason to have 2.7% of methane emitted across the supply chain. As we go from different fuels, that threshold goes lower. So if you want to use, there was a big push when we started this work to get to natural gas vehicles, and really it didn't consider any of these analytics, and in fact, it's the supply chain. Now, I personally got involved in this issue in a very simple way. When I was teaching at Brown University, I taught a field course, and we had purchased a natural gas van. I took out once a week with my students in the fall semester, and I realized I had no clue, because it was a converted Ford van, it had a normal gas gauge, how much gas was leaking from that. So it's a CNG van. We go fill it up, and I would have no idea if 1, 2, 3, 4, 5, 6% were leaking. If we're 20%, we'd notice because we keep saying it kept getting empty. And that totally affects whether, and we bought it explicitly to do the environmentally right thing. And it turns out when you do these analytics based on what the numbers that we had in 2012 when we published this, it was the environmentally better thing over 100 years, but it was net negative for the climate for the first 85. To my mind, that's not a policy solution. But if you just looked at the 100-year, the CO2e, you'd say it's better. That's the bluntness of that tool. It really doesn't do what we need it to do. So this is a context. There's some nice work you can integrate over time, but starting to think about all of the analytics as a continuous time variable. And at EDF, I started the conversation as we thought about climate post the defeat of the Waxman-Markey bill. It's all about time, time, time. Not thinking about it as one problem. What's the maximum temperature? I'm an ecologist. I work on forest impacts. I've written on the impacts of climate change on forests now for several decades. And I care a lot about the rate of change, the pattern of change, not just what's the maximum change. Because for a forest, that's what really drives it. And to do that, we couldn't use CO2e, we couldn't use the existing analytics. We needed continuous analytics across time. So we started looking at methane emissions across the supply chain. This is just a diagram from a paper by Adam Brandt in 2014 in Science. These are just the numbers that the inventory set at that point in time. So we needed to look across the supply chain, across the United States. There hadn't been any direct measurements made since the early 1990s, so we were really didn't have a good understanding of what was going on. So we started to set up what I think is a fairly ambitious effort for an NGO, was we were going to make the measurements and lead a campaign. But it was not going to be carried out by EDF directly. It was going to be carried out by academic scientists at a diversity of institutions. We ended up working with more than 40 academic and research institutions. And every study we did, we'd employ as many methodologies as we possibly could so that we could compare and contrast across those. That we'd have independent review wherever appropriate. If we had multiple teams, there was going to be a third-party scientific review. All the data would be made public, and all the results would appear in the peer-reviewed literature. So we undertook this effort starting essentially in 2012. And these are just the studies. Currently, there are 37 papers that have been published in the peer-reviewed literature, more than 140 co-authors, distinct co-authors from more than 40 institutions. And they're all posted on EDF website. So it's a large body of literature that we were able to assemble using a diversity of techniques, top-down, bottom-up, site level, component level, and I'll talk about all that in a minute. And across the entire supply chain with a little bit of end use. Now, what we didn't do is get involved in the end use, so I refer to it as the supply chain, not the value chain. We are currently having a major effort to deal with that end use as well. But at the time, it was more than we thought we could undertake. So these are some of the results just from the Barnett campaign, which was carried out in the fall of 2013, which was the result of a PI meeting among many of the people working on this issue, where they said, we're doing all great work, but we all have to come back one place at one time, a traditional field campaign. So we organized that. We had 12 teams in the fall of 2013, which also happened to coincide with the federal shutdown. So there were a couple federal teams, research teams, regrettably, that couldn't participate because they couldn't get travel orders. But we totally mapped the Barnett in Texas, which was the original area where extensive fracking took place, and separating biogenic from thermogenic, largely in this case with ethane to methane ratios. But the type of detailed maps, as far as I know, had never been produced in another part of the world, where we really understood the patterns of emissions across a diversity of infrastructure types and source types. And one of the things important to note when we think about these kinds of emissions is that we have, in this case, number of sites across the deciles of cumulative methane emissions, you have different curves on the low end, but you all basically see on the right-hand side that they're all fairly similar depending on where you are on the supply chain, and I'll talk about that in a minute in terms of the fat tail that's represented. And these are the kind of data that we simply didn't have until this type of work, this group work. So if we now plot the same data in a different way, looking at cumulative percent emissions on the y-axis and the cumulative percent of sites on the x-axis, what you see is a clear indication that you have a fat tail, that if you look at something like the production sites, you're seeing that 10% of the sites produce 80% of the emissions. So the good news in this curve is that a large percentage of the sites are producing almost no emissions. What we see consistently is that we know the technology can work, emissions can be low, but that on the other hand, there are a lot of sites where in fact that doesn't occur. So this was something that we found ubiquitous across geographies, across different components of the supply chain, that really allowed us to start to get a better handle on the nature of the problem and the total in the emissions. Now this is only US based. And then we had some part of the Barnett campaign, a couple of 3 different research teams characterizing the distribution of methane. And you see that if you start looking only for the larger emissions, if you do just a random survey versus one that's targeted to larger emissions, you regularly see that the fat tail is poorly characterized, which is not surprising. Being able to survey a fat tail is always more complex, particularly if you want to just take a random survey, because you're not going to see those sites very easily or very frequently. And in fact, what we saw in the data sets, if I think about the different parts of the data sets, if you did go out and do some random surveys as opposed to stratified random, what you tend to see is you find 2 or 3 big emissions on the right hand on the fat tail. But you don't have sufficient numbers to be able to characterize that fat tail effectively. I'll come back to this in a minute. So this leads to basically we need to start thinking about comparing the top-down and bottom-up approaches. Top-down to flying, as part of this, flying lots of aircraft. We did that in the Barnett and elsewhere. In the case of the Barnett, we flew more. A lot of it was from team from NOAA, but also others. And then doing a whole series of bottom-up facility-level measurements and comparing how well they come together. Historically, those kinds of measures didn't agree. And when you compare them for the Barnett, which was the largest number of such comparisons undertaken to that time, and I think still the largest data set, what we found is if we look at the top, you see the averages of total methane and fossil methane. They agree pretty well. But there's a lot of variation day to day, and the problem is if you take a single top-down measurement or even 2, you're likely to see variance just because we know there's a lot of variability over time and space and simply the lack of precision with making these measurements. But overall, we started to see for the very first time we could align it, we could explain where the emissions were and how large they were. And when we look at equipment level, which was done by some work done by Dave Allen and others, compared to site level, where we look at the whole site, and I'll come back to describing how we do that, what we see is that the components don't add up to the site, not surprisingly. It's no different than the problem the U.S. Census has. We currently have a total census, right? You have to go out and enumerate, count everyone. They have proposed, I've forgotten now, for the last census, I believe, that they would use a statistical approach to finding the hard-to-find people. And the Congress refused. The reason the Census Bureau wanted to do it, it's much more accurate. So we have the problem if you have to count all emissions, and you know you have fat tail, and you know you have these things occurring but very infrequently, that's a hard thing to count. You need enormous sample sizes with enormous effort, where if we look at whole sites and go to a large number of them, you get a far better characterization of the overall emissions. And this is the difference we observed. Really important distinction, because in fact, always all the inventories are done as equipment level, sum up emission factor towards inventory without a fat tail, sum them up, and that's how much the emissions in the U.S. or anywhere else are. That is the standard practice currently to date. All the data you're going to find online is done that way. So if assuming that you have reasonable underlying data, it's a low estimate by definition. And what you in fact miss, this was a paper in Nature Communications, and again, all of these papers are available online at EDF, and there's, as I said, there are three dozen plus of them. is we can explain it, except for we end up for the unintended emissions at the higher levels, what I'm calling the super emitters, that are totally missing from the inventories. We have by design, there are some emissions that happen because they're designed to work that way. Some of those can be large, many of them are small, and then you have the ones where things are broken that people are known about, and then we have this whole new phenomena we'll call the super emitters, which become critically important to being able to estimate the total emissions of methane anywhere in the world, but here we're talking about the U.S. All right, so that's the first phase. We put all that data together. I want to talk just a second about this mapping that we did with Google. In this case, this is a Street View car, and they said, let's work together, put a methane analyzer in the back of the car, send it out driving. The driver in this case is a driver. There's no scientist there. Their job is to drive, nothing else. And what we worked out in an arrangement with Google and EDF, we take no corporate funding. So in this case, Google contributed their part. We raised funds. They did the driving, equipping the cars, providing the driver, upload the data to the cloud. We grabbed it, did the science to turn that into actual maps and quantification and do the publications. In the case of the work that I just described, there were some corporate partners in that. They contributed. It all went to the academic partners. So we raised all of our money independently. EDF, for that work I just described, the total project was about $20 million, and EDF raised from philanthropic sources about $12 million. Companies put in about $6 million, and then the universities contributed and research institutes contributed in kind of several million. So we started to drive around the United States to quantify emissions from local distribution systems, and the goal was, again, to make all the data public. And here's the website you can look. You see the results from Boston as opposed to Indianapolis. Indianapolis made a commitment about 30 years ago to replace all their pipes. They're all new pipes. And you see that the number of leaks as opposed to Boston, where you have old pipes, and there had been previously, since changed, the Public Utility Commission only allowed a 40-year replacement cycle, and it was very difficult to get permission to dig in Boston because of the disruption, so the utilities were not able to change the pipes very rapidly. That's all changed now. They have a much more accelerated pipeline replacement program. And this just gives you the patterning that we were able to do. These are publicly available. There are 15 cities. Well, I think we have 12 posted. There will be 15 soon. And the size is indicated. Now, as we thought about this problem, every instinct I had on how to present this data was wrong. So we ended up doing a whole series of experiments with one of my staff, who's a social psychologist, on how do we give this data to people so that they can understand what it means. And if you can read it, if you look online, what you see is the description is the size of the leak equivalent to miles driven and its impact on the climate. That was done because if we refer to the gas that's used to cook meals, that leads to people to thinking about safety and explosion. And if there was any dangerous levels, we had protocols like anyone else should. They got called immediately to the emergency repair line at the utility, and they went out in the field, checked it out, and fixed it if, in fact, they found something. But these maps are created by driving at the speed of traffic with an instrument in the back with fully automated upload, data processing, produce the map. Requires 2 drives to confirm the way we work it to ensure we don't have false positives. For example, if there's a CNG vehicle going by, it leaks gas, and so you could pick up that leaking gas as an indication of a leak as opposed to, in fact, a pipeline leak. And so these maps are available, and now the Public Utility Commissions in numerous states require that these kinds of data are part of the prioritization. If you simply take your existing repair program or pipeline replacement, using this data, you can halve the methane leaks at no net cost. So that's a pretty good deal. And these just gives you the density of the two. In Boston, 1 mile per leak indication. In Indianapolis, 200 miles per leak indication. Big difference, policy. How do we get those aligned? By giving the data to the Public Utility Commission and utilities. Many of the utilities saw this data and have just grabbed it and run with it and recognized that this is a tool they can put in their own arsenal of things to use to do their job better. We will be. Yep, go ahead.
The gap between Cambridge and Somerville.
We didn't drive there.
It's a sample.
It's a sampling, right? Yeah, and if you go on the map, it shows you exactly. These are blown up so much you can see exactly which roads were driven. So you know the absence of data if it really means there's absence of leak or it's absence of data. So now I want to shift to the synthesis, which we published in Science this past June, which was really to try and coordinate all of this work we did and bring it together into an overall summary of where we stand on methane emissions in the United States. Now, I should say the data I just presented, which again is the work of dozens of institutions, hundreds of scientists, is the best such database in the world, period. There's no place in the world that we have data like we have in the United States at this point, not even close. So we wanted to bring that all together, comparing the site level, quantify overall emissions in the U.S., through to the meter, not including the value chain, not including the use of it, which is an important piece, but we just didn't have enough data at that point. And we wanted to compare site-level measurements with top-down measurements. So comparing surveys for 9 basins with well site, and there were 24 co-authors from 16 institutions, and we wanted to do it across the supply chain, as indicated here. This is just a list of the diversity of co-authors and their institutions they were associated with. These are the basins that the data that were used for this synthesis come from. They account for 33% of the gas production in the U.S. and a quarter of the oil. So it's a darn good sample size, I would argue. At least in my world of forest ecology, I don't get to sample a third of much of anything. I have to extrapolate from much smaller. And the methods, as I mentioned, was really looking at production at these site-level measurements, not the component level. We do that as well, but that's another comparison. But site level, as well as some of these studies that were part of our story, and then sum that together, and then independently look at the top-down estimates and compare them directly. So totally independent estimates, and see how well they do. And then ultimately compare it to the U.S. EPA greenhouse gas inventory. So 3 levels of survey, and I want to talk about it because this becomes important. So the basin level with the aircraft, the site level where you're doing drive-by, so these are with no permissions, you just literally go by on a road or downwind, anywhere you can get downwind, you make an estimate of the plume of methane coming off the site, and then determine the total emissions from that site, versus the component level where you look at emissions from each component and sum them together. And just as an illustration, because this is a point that probably this group understands better, that difference that I've struggled a little bit with. And the metaphor I use, metaphors are always problematic. If I want to know the height of this house, I can do it 3 ways. So I can think about it in the way that I had to solve. I put in a tubular skylight in my house, right? You put it on the roof, and I wanted to bring it down the first floor to the kitchen. You have to figure out how much tubing do you need. So you go up and you do the attic, and you add up how big is the joist, and you add all the pieces together and say, this is how tall it is. It's a pretty low precision and a pretty low accuracy approach, because I have to add all these pieces together, of which there's compounding errors, but it's a way to do it. Or I can just simply put up a scaffolding and measure it with a tape on the outside, or I can go down the street and use some geometry and estimate it, kind of remotely. So we have those 3 approaches we used for methane across the United States. And when we compare them, so we'll use the site level emissions and the blue versus the EPA inventory. What you see is we find more emissions than the U.S. inventory. Not surprising, because they're using component level, and when we do the component, I won't show you the data, we see the same pattern. And a lot of it is in the drilling and production. That's where the amount is more than double what EPA is estimating. And part of the reason that the gathering and processing and transmission and storage, and absolutely the local distribution is because they'd already started to incorporate the data from our studies. So they'd already brought a lot of the data that we'd collected in, so by nature they're going to be converging. And when you look at them by component, this is basically the same data. We're talking about a 2.3% leak rate in the United States, as opposed to the EPA's estimate of 1.4%. So there's a lot more gas. There's also a lot more opportunity to reduce those emissions. And as you're probably aware, there were regulations put in place at the federal level to begin to reduce emissions. In the Obama administration, there's an effort currently in the Trump administration to reduce those regulations. There are state-level regulations in California, Wyoming, Ohio, Colorado that are directed at doing this. And obviously you can tell from that it's not a blue or red. It actually crosses political boundaries in the sense of the dominant party in charge of those states. And when we look at the comparison of the top-down and the bottom-up across these different basins, what you see is the agreement is pretty good. So that's top-down minus bottom-up over top-down. And the really big ones, Haynesville, Barnett, Northeast Pennsylvania, San Juan, Fayetteville, work pretty well in the Bakken. There are some major discrepancies in the Uinta and in the West Arkoma, but those are smaller basins, and there are still work to be done to figure out why those disagree. But in the case of the Uinta, that's a single flight. So it could be simply you've got a bad day and you're getting differences. They're not statistically significantly different, and the overall emissions are certainly not statistically significantly different, though the top-down is slightly higher than the bottom-up. Again, bottom-up in this case is site level. And when we look at the distribution of these two, a bottom-up versus top-down, you see that they're very overlapping, though the means are slightly offset. So the takeaways. We have higher oil and gas emissions than official inventories. We have seen the same thing and published it for Canada now, and the Canadians have passed federal legislation to reduce those emissions. We have completed and are about to publish results from Mexico, which also has proposed regulations. So North America, there was agreement among all of the presidents from all three nations that they would attack and try and achieve a 45% reduction. We see abnormal conditions responsible for a large proportion of these emissions. So the good news is that gives you a good opportunity to reduce them. And in fact, the International Energy Agency, in their report last year, their World Energy Outlook, said that they estimated that 75% of methane emissions can be mitigated, and 50% of emissions can be done at no net cost. So most of the fixes are not even costing anything. It's about just doing things better. And again, going back, if we look at the left side of the curve consistently, a third or so of these sites are essentially clean. They have small emissions or no emissions. So the good news here is we know how to do it. We demonstrated we can do it. And now we just simply need the will or the regulations to ensure we do that more broadly. And that a lot of these malfunctions are not understood. They're not recognized. When we did a survey of 1% of all the well pads in the United States, we found roughly 4% of the sites had large emissions, and those are largely unknown. They're coming out of tanks. They're coming out of upstream problems manifested in the tanks, and they're not recognized. That's the big players, the majors, the mom and pops, and across geography. So this isn't just like, which is traditionally, the big guys point at the little ones and say, we're clean and they're the messy ones. That isn't, in fact, we have the data to say that's not true. That isn't to say that everyone's equal, but it isn't one segment versus another, and it's not just upstream, it's across the whole supply chain. And that there are actions that can reduce emissions that are clearly demonstrated in places where there have better, through monitoring and through regulation, you see a reduction. And if we did root cause analysis, we know we should be able to fix these problems. And I'll use the metaphor again of aviation. We get on a plane, we have a very low risk of crashing. Not because planes haven't crashed in the past, but But every time a malfunction happens, they're required to figure out why, and is there a way to avoid it from happening again. They do that root cause analysis. Their engineering's great, and it basically has become a very robust system. But we do none of this. We have no data on why did a leak occur, why did emissions occur, so you don't get the learning, so you don't prevent it from happening again. We need that kind of root cause analysis. I personally believe with that kind of analysis, the cost to the companies will actually be lower than they are today, because you get a lot better at preventing it and you don't have to fix things. And then also from a safety standpoint, it helps when the helicopter team was flying across those 10,000 well pads. In 3 occasions, they saw such dangerous situations they had to literally land and go and warn people. A house in a big cloud of methane, workers in a big cloud of methane, and I've forgotten what the third one was. So just switching briefly to the global situation, this is the United States, but there's oil and gas produced around the world. And if we just look on the left side, we see the countries with emissions, estimated emissions. There's the number of countries, roughly 10, accounting for 80%, as best we believe. But very little of this is based on empirical data. We need a lot more data. We're actually working on replicating what we did in the United States across the globe to collect that empirical data. And this is just a map of a project we're doing with the Climate and Clean Air Coalition, which is part of the UN Environment Program, and in collaboration with the Oil and Gas Climate Initiative companies, which is now 13 of the world's largest oil and gas companies that produce directly about a quarter of the world's petroleum and gas production. So we've already initiated a series of studies. I serve as the chief scientific officer. The companies are involved in the broad strokes of what we do, but not directly in the research, and we follow the same principles. These are led by principal investigators that are independent. They have full control over their science. So these are a good length distance between the companies and the data collection to ensure it's independent. And we're ongoing and continuing to work on this. And then it's a big deal. This is just some of the remote sensing and looking at what was happening in Aliso Canyon. You may have heard about it a couple years ago, happening in California, where there was a blowout at a natural gas storage facility in Southern California that created the largest leak of methane in the history of the U.S. And it didn't get a lot of notice until it's not particularly good on the left. You see the infrared image. If you do it in real time, that image then got all the news media excited. That was one of our staffers who got in a plane and flew it with an IR camera to say, this is a big deal. I mean, it was reported, it just didn't get much traction. And so, of course, California has since developed very strict regulations to control it. But we can think about this is happening every day around the world, maybe not as dramatically as this one, but there's exactly this phenomena happening in thousands, tens of thousands of places around the world. And in order to address that, we are in the process of building Methane Sat to be launched in 2021, which will give us an unprecedented ability to map methane emissions quantitatively across the globe. We are initially targeting oil and gas sector, so our mission includes being able to have regular quantitative mapping of emissions from 80% of global production. They will be able to see other anthropogenic sources, and we expect to look at those, though initially we're going to focus on oil and gas because it's the low-hanging fruit, because it's basically so much of it is no cost or low cost, and the existing technology is there, so let's get rid of it. The science is being led at Harvard. Steve Wassey is the PI you might describe on the mission. Steve and I have been talking about this for numerous years. We've been working for 3+ years on it. We've raised the bulk of the funds needed. It's going to be a philanthropically funded endeavor and commercially built. So we're sort of hybridizing between academic and commercial sector satellites to produce Methane Sat, and we're excited by the potential and the ability to produce it. All the data will be publicly available. All of it will be policy relevant forms, so our derived product will all be quantitative flux maps. and happy to answer later any questions about methane sat. I do note funding. We're totally transparent. These are the sources of the majority of our philanthropic funding, which are also listed in all of our publications. So thanks very much. Yeah, so the spatial coverage, low Earth orbit.
I'm sorry to interrupt you. We have 41 participants online, so if you could
repeat the question. The question is, can I give some more specifications about methane sat? So it's a low Earth orbit. It'll have a precision of 2 parts per billion, which is ambitious. We will release many more details at the beginning of next year. We are finishing up a competition among commercial vendors, so I can't get into all the details. It'll have a 1 kilometer pixel size. It'll have a 200-kilometer swath, and we anticipate return interval time of roughly every 4 days for the oil and gas infrastructure globally. I don't know if there's anything else specific. I'll try and answer if I can. But we'll be totally transparent, but because we're still in this sort of sensitive phase until we get those contracts drawn up and everybody's, the down selection and final contract. But the thing that was really exciting to me, so we sort of thought this thing up, and what we did a little bit differently than is often done is we actually started with the Barnett data and said, what would it take to be able to accurately met the Barnett, which was the best data set we had for any place in the world, and then went to the technology and say, can we build it? So we started, what do we need? And then, can we build it? So that's how that process went forward. I don't know if there's any other specifics. No, that gives you a sense. Yeah.
Well, as a follow-on to that, you said you have a number of bids from private companies, so you haven't settled on a specific technology in the measurement.
So we developed a technology strategy and then asked the companies to how would they implement it. And the really exciting part is we had multiple vendors who everybody went, sort of took a deep breath and, when they heard what the spec was and could they really do it. And then we had multiple companies come back with actual strategy for meeting it, which was really exciting. Though it was also a challenge because we had to reduce it down. So we did come in with a strategy for how to do it. I mean, it'll be a hyper spectral approach, not too surprising.
We have a question online.
Yep.
A little long one, so I'll try to. So Eric Wolwoski, he comments and asks, so in a study I conducted on life cycle greenhouse gas emissions, we determined that the overwhelming amount of greenhouse gas emissions comes from the consumption. Is there a significant enough benefit from extracting oil and gas in a more climate-friendly way rather than exclusively focusing on switching to energy production, which will not contribute or will contribute significantly less to greenhouse gas emissions at the consumption stage?
So the question is, should we just go straight to lower carbon emitting energy sources versus cleaning up the supply chain? I think the answer is unequivocally, absolutely, we should collect up the supply chain. I don't know of any pathway in the next 5 years to get rid of fossil fuels. And given that methane, we should be able to reduce, literally with existing technology, alternative BAU temperature by 0.2 of a degree by 2050 by cleaning up methane now. So, and I know of no way to substitute for that. So it's an and again. Should we reduce fossil fuel use? Absolutely, as fast as we can. But the pathway, even if you're aggressive, is still long enough that the methane associated with those emissions and reducing it not by simply using other fuels or other energy sources results in a large benefit to the climate over the shorter term. Because most of these reductions can happen in literally a couple years. So you could reduce significantly. You could probably reduce methane emissions if there was a global will to do it. You could probably reduce methane emissions from the oil and gas supply chain in half over a decade easily. Because again, the technology is there and it's cost effective, which is a little different than CO2, where there are many things we can do that are cost effective, but we can't get the whole way to a totally zero carbon economy with currently cost effective technology. We can do a portion of it and then we run into and then it will be to be determined. So I think it's incredibly important that we do both. Reduce fossil fuel consumption as soon as we can and reduce the greenhouse gas emissions from producing it. And also remember, as if there's a big difference between the, if you reduce the methane emissions from oil and gas, it makes it, in the near term and the long term, incredibly more climate friendly than coal. So the degree that you need fossil fuels, there is a hierarchy among them with respect to which ones would be preferable from a climate standpoint. So you would never want to keep burning coal while you try and reduce gas, even if it were somewhat leaky, but you don't even have to make that trade-off. You can make it tight and get rid of coal in the near term and use other fossil fuels, and you're going to have a very strong short-term positive impact on the climate while you're reducing the total carbon emissions. Yeah.
A lot of emissions happen over water with gas, not just production, but also floating production storage units, and more with LNG transport as a global resource. And as I understand it, but I'm not at all the measurement expert, it's much harder to decipher emissions over water. Is there and you can't do site visits as easily over water either.
Actually, you can. We do site. Actually, we do site visits.
But in transit, like if it's, a bunker
Sure.
that's moving. So I guess you could track those too. But will the methane sat be able to measure methane?
We're not assuming. There are some techniques for doing it, but you're absolutely right. It's much harder to do it over water than it is over land. And but don't assume the overwhelming majority of the emissions are over land, not over water. So there is a piece of it, but it's not, relatively speaking, as large. It's not that large.
And even with LNG?
Even with LNG right now is still a very small part of the supply chain. And how much is coming off the ships? We've got a project right now with the National Physical Laboratory in the UK to measure some of those things. There's not good numbers on LNG production and transport, and so we're trying to collect those. So that's part of our big international study. We also are running a whole series of surveys of offshore platforms. We've completed it in the Gulf of Mexico and the North Sea, and those data will be reported out pretty soon. So is it an issue? Absolutely. And should it be redressed? Absolutely. But it's still, relatively speaking, and we'll have final numbers to quantify it, is smaller than it is for the onshore. James, and then there's a question in the back.
I was wondering, given that the lifetime of some of this natural gas and oil production or production and distribution infrastructure can be decades, I'm wondering if a lot of effort were put into just kind of replacing and updating the infrastructure rather than just switching away from natural gas. I wonder if that would just kind of prolong the use of natural gas because, for example, if you were to replace all the old leaky pipelines in a city with new ones, well, that might be an investment that's kind of not worth making if you want to transition away from natural gas.
So great. I mean, in terms of the infrastructure, for the most part, we're not advocating more infrastructure. I don't think you need it. In most cases, you can repair it quite easily. The majority of the natural gas low pressure local distribution pipes have already been replaced. I should know, but I don't off the top of my head remember what percentage it is, but it's a relatively small percentage. The challenge is what comes next and how long. So at a minimum, you want to repair it. And in some cases, you want to replace it because it's not clear that we have an alternative path to get away from gas. Other people are also talking about using biogas in those pipes so that you'd actually move biogas around. And, if you're going to replace them over the next 20 years, I mean, there is obviously a point at which you say, hey, but you have to have a strategy for how you're going to not use the gas, and particularly in places like the Northeast where a lot of those leaky pipes are. You're using them for residential heating, and you don't have clean electricity to be able to convert them all to resistance heating or heat pumps or geothermal. So I think, but it's a great question. I have spent some time. There have been some projects that various universities have taken on of how much investment you make before it becomes counterproductive, and figuring out where that sweet spot is. But it's something absolute. So in terms of long-distance pipes, in terms of that kind of infrastructure, absolutely. There are some strategies for how you can actually use the existing infrastructure more efficiently. There's some artifacts of how they do it. You reserve capacity. It's not the volume that's in it. So there's unused capacity in pipes when they're at maximum. So when they're having to shut down the factory, the pipe is usually not full because someone's reserved the capacity as opposed to use the capacity. So there's some actual policy instruments that allow you to sort of increase your flexibility without increasing your pipes. The local distribution, though, is a little bit different. In the case of the pipe, it was in front of my house, which was replaced about 5 years ago. It was over 100 years old. It was put in the ground for manufactured gas, not for natural gas, which has some different composition issues. From a safety standpoint and from an integrity standpoint, I'm not sure I was willing to live with that 100-year-old pipe for 30 years or however long it takes to get everybody off, because it did represent a safety issue as well. So it's not just the environmental integrity, it's also the safety. So we had a question in the far back.
Yeah, so you mentioned the Google car. I was wondering what organization sponsored the aircraft that observed and measured methane emissions?
So a lot of the work was done by a team out of NOAA. There's a group, Scientific Aviation, that I actually contracted with out of UC Davis. Steve Connolly, he's the one who actually quantified from the air the Liso Canyon. He's done a lot of work for us and others. So we funded, EDF funded a lot of that work, NOAA funded that work. There's been a host of organizations that have funded the top-down work.
Okay.
So we didn't fund all of the comparison and the synthesis. We contributed to quite a few of those, but not all of them. And there's several teams. I'm sorry, I'm having a senior moment here. I'm trying to think of the researcher. There's another researcher who's done a lot of, Paul Shepson, who was at Purdue, who's now at Stony Brook.
Yeah, I worked with him previously at Purdue in that same group. So.
Okay, so Paul's done a lot. Steve Connolly, Colin Sweeney. There's a diversity of folks who've done those kinds of measurements, and that's really matured over the last 6 years. So it's really become much more routine. Online question?
So, Alex Turner from Berkeley.
Yep.
Great talk, Steve. I know that California is also hoping to launch a satellite potentially in CubeSat. Do you have any thoughts on what kind of satellite or measurements will help complement the EDF's Methane set and NASA's EOCAR satellite? Basically, what type of measurements do you think of the make to complement other satellites?
So the California satellite, and again, it's gone through some evolution and they're still evolving it, is a target mode satellite, which means it's going to be having a much finer pixel resolution, much narrower swath, which fully complements the work that we're doing on this larger mapper, which we'll be able to quantify for these larger regions, even if we can't pinpoint sources. So the California satellite, as it's been envisioned in the conversations I've had with them, I see that as a very complementary mission. The kind of data that we would produce would give them the place to look, because you still have to target it. Where are you going to look? And because of the narrower swath, that's going to have to be a constellation, so that'll take a while to get to the point that you'd actually have the kind of robust coverage. Trying to think, there was another part to the question that I don't remember now.
What type of measurements do you think California could make to complement the other efforts?
Yeah, so I think the main thing there is just to identify point sources. And there's also GHGSat, which flew a satellite that they're now flying a new one. It had some precision problems. That's a commercial satellite. The distinction between what we're going to do as well as California versus GHGSat is all the data will be public. And it won't be for the commercial satellites.
Follow-on, we have Jordan Turner. Steve, great talk. How do you envision the information?
And Jorn should say, because he's from the California team, he's heading it, so he should answer this, not me.
The information from methane sets to be turned into action on the ground.
Yeah, so we are developing an advocacy program that goes along with what we're doing. So not just presenting the data, but just as we've done with, I talked about the local mapping. We had a whole team that works with public utility commissions and utilities. In the case of the studies I showed you, we have 5 EDF scientists who helped with that, PhD scientists. There are probably 35 people who work in intersecting with the states, the federal government, now with Canada, with Mexico, and how to develop the policies that follow on from the data and what they indicate. So the key is to have a large team that really can work with the different jurisdictions, the different types of organizations. We also have worked on, there's investors' guides, so how do they use it? So working with the investor community, working with the oil and gas companies. And so we have teams working in all of those venues to try and use this data to more effectively accelerate the uptake of the learnings and ensuring that, in fact, we're driving emissions down. And I think one of the things that's really exciting is the large number of oil and gas companies. Just in Climate Week in New York last month, they announced their target, the Oil and Gas Climate Initiative companies, that the portion of the supply chain that they're responsible for, they've made a commitment that their emissions will be 0.2%. So we applaud that. We will do everything to help them get there. But that is think about, remember what I showed you from production in the United States. We're talking about 1.8% going to 0.2%. So if everybody in the industry does it, we are got a very long way to solving this problem. So we have to work across those different communities. And that takes people working directly with them.
One last question from Heather Raven, California. There's a lot of interest, a lot of people from California.
Yeah, there's a lot of great work happening in California.
Do you find the large urban or well path leaks to be temporarily variable or intermittent?
So there's not as good data as we'd like, but there is clearly a stochastic nature to them and an ephemeral nature to them. So it's not once you start leaking, you continue to leak always. Some of it is ephemeral and stochastics, which meaning they're moving around and not staying put. And so, but we need more data. And one of the things we think we can do with methane stat is on the larger regional basin, we can actually look at temporal dynamics because we'll be able to go back repeatedly and keep saying, does the aggregate emission stay constant? Doesn't mean that's always in the same place, but it's basically a constant pattern. Or does it, on the aggregate basis, go up and down a lot? And we do not have that data for any place in the world right now. The Barnett data, the flights there, I think, is the richest data set. There may be some others now. I'm not aware of them. But that only begins to give us a glimpse at the temporal dynamics across these basins. And that's become critically important. At the site